Hey everyone, welcome to CTCI136. We have a lot in store today. As our presenter, Dimitro, will be going over everything you need for a tech interview. From arrays to heaps, we've got it all covered. And be sure to stay tuned for the end because we'll be going through a mock interview where I'll be giving Dimitro a question and he'll be using everything in the slides in order to answer that question and demonstrate exactly what you need to do. So as always, the Slido link is above if you have any questions, and I'll monitor that throughout the presentations. We'll answer the questions at the end in a Q&A. And if you want to follow along, the bit.ly to our slides are also above. Anyways, enough on me. Dimitro, take it away.
Okay, yes, very good. So the title of this talk is Cracking the Coding Interview 136, and that title is apt because we will be talking about technical interviews and mostly the algorithmic sort. There are interviews, especially in lower terms, that are focused more on behavior. Unfortunately, it's very difficult to give conclusive advice there. Recruiters disagree on what constitutes a good behavioral question answer, and students have conflicting advice. I will talk about that, but that's not the focus. With that in mind, let's jump in. Okay, so interviews normally are half an hour or an hour long. That mostly just influences the number of technical questions you'll get. They follow roughly this structure right here. At the beginning, there's some light chatting. Usually you tell about yourself. They tell you about the company. You have behavioral questions, often at least one question about behavior or your past work. Then some number of technical questions, maybe a lot more depending on the kind. Too, and at the end, they usually ask you, they leave some time for you to ask questions. That's a typical structure. Now, when you talk, actually, let's use this because this has all the information here. So when it comes to these questions, such as talking about yourself, actually, let me go back because I haven't covered everything here. So when you tell about yourself, my personal advice, this is subjective, obviously, but if you are lost for options, I just do everything purely technically. That works. I haven't had much complaints. Usually I have good response from interviews. The questions at the end are important. You should ask some. I've had bad outcomes with not asking any questions. And with behavioral questions, it's important to realize that they shouldn't be interpreted literally. Like often behavioral question would be sort of what's the most difficult bug you've solved, or what is, let's say the most difficult challenge you faced before, what's your main weakness, and all of those questions. You might be tempted to interpret at face value, but the point is always that you should tell a good story. That's my advice, and you should obviously pick the stories which have a good, successful ending. So truthfully, in one of the cases I've had, where I would talk about my past internship, truthfully, I would have to say that the most difficult part of that internship was that no one in my team seemingly understood the direction of the project and what the stakeholders wanted, and we did a lot of redundant work, and there was a great deal of confusion. But that's not a good answer to that question because we didn't solve it in the end. I just left, so there's no happy ending there, and it's boring. It's a boring story. There are no interesting details. But a good answer would pertain to ideally to what the interviewer is interested in. For example, I in the past had interviews with someone who worked with Golang, and I knew some sharp edges of Golang, and I made an answer that wasn't really a lie per se, right? It's just it wasn't really the most difficult challenge I faced in my past internship, but it was about a particularly difficult debugging situation that did arise. It wasn't the most difficult bug, but it was an obvious sharp edge in the language. And the interviewer knew about it, and he commiserated with me, and that was a fun time was had between us. So that I think is the direction you should go with those questions. Other than that, I have to caution you that you should expect questions about things on your resume, sometimes very in-depth questions. I've had experts on specific technologies I've used ask curiously about them. So you shouldn't put things in your resume that you don't really know. It depends, it's a bet, but it's a risk. Ideally, you should know all these things. I found it very fruitful to spend some time researching the company you're interviewing with and your interviewer beforehand. And when interviews were in person, usually I would come to Datum Center and spend only about an hour, half an hour, sorry, researching the company. And sometimes I wouldn't know anything about it, and in that half an hour, that was sufficient for me to learn enough to handle myself in the interview. And if you know the interviewer, then one particularly good strategy is to look at the company's blog, if they have a blog, and the interviewer might have posts there, and then that would give you a good idea of what to expect in the interview and some common points that you can touch on. I did that to great success in at least one case where the interviewer did actually have regular blog posts. Now that said, all these things, behavioral questions, etc., you should try to condense them as much as possible, leave more time for coding. I haven't really felt often that I had way too much time on my hands, so be cognizant of that. I already mentioned that you should tell a good story in behavioral questions. That's that. And that you should ask something at the end. And if you have no idea what to ask, there are questions that work all the time, pretty much. I usually ask at least for them to give examples of what past interns did if they had past interns. I think that gives a good idea of what your work would be like, and it's a reasonable question, one you can always use. With that said, let's move past this to technical questions. And there's this great guide by Jennifer from the CS Club Discord that I just adapted to this presentation. This is sort of step-by-step structure in case you totally blank where you see a question. This gives you something to follow. And even if you don't, it's a good thing to look at it, keep in mind. You shouldn't, I won't read this back, of course, you can read it, but the general theme is that you shouldn't jump straight into solving a problem. Even if you know the problem, if you've seen it in LeetCode before, you think you know well how to solve it. It's always best to walk through, say, this is how I understand it, this is how I intend to solve it, sort of my approach. And the reason this is valuable is because it's often easy, in particular, to pattern match a problem wrong. You think you've seen this one, but it's subtly different from what you've seen. And that's a bad thing to show that you're inattentive to details. So always do that. It doesn't take long. You can spend like a minute going over that and then jump into coding. And it is important to write test cases at the end. So some people will tell you not to. They say, don't bother, this is fine, I see that it works. But you should ask, you should always volunteer. And that initiative will be seen in good light usually, and test cases will show that you care about details. You should include some edge cases there. If you have time to do more than one, you should show that you understand where the problem is difficult, where a solution can fail unexpectedly. But that is the general outline. And specifically also where I say, you should discuss the problem beforehand, you should not stop talking about it as you solve it, right? You should keep, I try to always just not shut up during the whole interview. I pretty much talk incessantly as I do it usually I do it on the whiteboard, which is different from online, but online also that works. You can just type and talk as you type, and I just directly dump my thoughts into voice medium, and that works very well. I've had good experience with that. No one said I was too chatty, or I didn't get impressions anyone thought that. Now, specifically, what you might say as you go through a problem in your interpretation, it's good to show that you understand sort of how problems work in the sense that depending, you might ask, for example, how big can the input be, and that might influence your choice of approach. So it's good to shows you're cognizant of how input size affects the problem. If they say, for example, oh, your input can be arbitrarily long, or like billions of elements in an array, then you have to understand that means that your algorithm probably should be at least like linear, or at most linear, or linear logarithmic, right? N log n. And it's good that if you voice that. If you see a bug, you should just immediately point it out, right? If you're right, you shouldn't like pretend that you didn't notice it and then fix it silently, because the interviewer is spending all the attention they have on your code, so they probably have seen it and they also know the correct solution. It's good to just point it out. Oh, I think I did something wrong there. Go back, fix it. That's fine. That's shows in a good light too that you noticed it. That is more or less it. And an important point also is that in all interviews I've had, pretty much all of them, if there was anything algorithmic at all, time complexity came in, right? They won't just ask you to implement this and then move on. They will ask you, okay, so what is the complexity of your implementation? Is this the best you can do? Can you do better, etc.? So that's important to keep in mind. And we'll come back to complexity in a moment. But what really the interviews concern themselves with is actually a pretty short list of topics. And the reason I want to point this out right now is that, really from this point on in my talk, if you have competitive programming background, right, then I think you'll be, you won't find anything new to you, because all these things are pretty standard, really basic, I should even say, for competitive programming, right? If you compete in like CCO and higher, but that is good for you as an interviewee, because you get to really show off your skill without getting bogged down in difficult details. And this is why I can make this short list of things. Like I was never asked really difficult data structures. Some people say, some people do get asked difficult ones, usually with the companies that are known for difficulty of their interviews. Like Jane Street maybe will ask you something really complicated. Most companies just limit themselves to these basic ones. And the same kind of goes for algorithms. I make this, by the way, I make this distinction between data structures and algorithms sort of for a reason, because some say that data structures are real fundamental to problem solving, and you just have to pick the right data structure, and then your logic flows out of it, more or less. And that's generally true for many problems, but there are some questions which are really not, I would say, not really. It would be a stretch to tie them to data structures. And the most annoying kind is the second one here, which is the ad hoc problems. For example, what I mean by that, I list here the XOR trick. That trick is the following. You have a sequence of n-1 distinct integers in the range 1 to n. So that means that 1 is missing, right? Because there are n integers in that range, and you have n-1 in your sequence. And your task is to determine which integer is missing. So that problem, you can do it pretty easily, right, with a set, let's say, but or not even a set, right, an array of the same size, or a track if you've seen elements. But if you are constrained to use only a constant amount of space, then it becomes less obvious. And the trick is that you can use the property of XOR, that a number XOR itself is 0, right? So you can XOR all the integers in your sequence. You can XOR all the integers from 1 to n, XOR those results together, and you get the missing number, because everything was XOR twice except that number. And that's the kind of questions I don't like, right? Because if you've seen that trick, you have a way easier time than if you haven't, right? They don't really test problem solving very well. They test, have you seen a lot of tricks in my mind? And this is why we won't go over any more of these problems in this talk, because there are really too many of them. They're all different. You should just go look at LeetCode, and you'll see plenty of them, and that's it for those problems. But we'll go over everything else in this slide. Actually, and speaking of LeetCode, it's a good resource. There are at least 2 good resources that more or less everyone I know in my program use these at some point. They're popular for a reason, because they really do reflect the kinds of things companies ask. In fact, LeetCode, for example, I've had problems verbatim from them, from there. And there are some users create sort of listings of problems that are asked by a specific company. They are not necessarily accurate, but I've had good luck actually with them. One of the companies I interviewed with had a list of like 20 problems there, and I was asked a problem exactly from that list in the interview. So it's probably a decent investment of time to actually focus on them. And carrying the coding interview is just a classic. I don't know what else to say. More or less, or everything we'll go over here is more or less contained in there. You can refer to it and skip the rest of the talk. Most of the rest of the talk will have something that's not in there, so be careful about that. And also in the slides from this point on, there will be numbers and parentheses, and whenever I mention these numbers, that those numbers refer to LeetCode problems, because I mentioned a LeetCode problem. So it's easy for you to refer to that. Okay, so the first, I guess, specific topic to cover is, as I mentioned, time complexities, time and space complexities, really, because that is something you will almost inevitably face in your interview. And CTCI, the book I just mentioned, goes over that topic in great detail. I won't really go over it in great detail. You know, this is an example. You sort of should be comfortable with this level, you know, of complexity analysis. Not much more will be required of you, but it's important to sort of keep track of your, one important thing is to keep track of your variables, right? When you, or, you know, when people say, you know, something is O of n, what is n there, right? It's important to be very precise about that, because here's an example, right? You take an array of strings and you sort them and you print them in order. Well, it's easy to say that the complexity of this is n log n, right? Which is the sort of where n is the length of the array, but you forget then that strings, you know, it's not constant time to compare strings or to print strings. So you should do something like here, where you say, and also m is the length of the longest string in the array, and then this becomes true. And it's kind of important. Interviewers usually will want you to be at least this precise with your O, sort of big O complexities. And when you start doing a problem, one reason this is useful is that it helps also inform your choice of algorithm, choice of approach. You know, when you start on a problem, you can probably immediately spot a naive solution. And it's good to voice it, sort of say that, oh, you know, it obviously can do this, maybe that's very inefficient, and say exactly how inefficient it is. And maybe it's actually a reasonable solution, right? You can say, oh, if n is small, then this is reasonable, right? It's not like exponential, and n is just quadratic, so it's reasonable. But there may be a better solution. And how to find a better solution is well, difficult, because that's the whole substance of the technical question. But you at least can use a different kind of argument to also figure out how low can you possibly go. Because it's not useful to optimize your solution. In some sense, it's not useful. There are still constant factors, so you can mention that. Some companies will appreciate that, but generally, it's not crucial to optimize your solution beyond, you know, what is the lowest possible asymptotic runtime. For example, here, if you sort things, right, then everything else will be at least n log n, right? So that sort of gives you some freedom in the rest of the algorithm if the sorting is really crucial. And more generally, or sort of more purely, if you didn't know if sorting was crucial, it's important to, or it's maybe helpful to give yourself some worst sort of some lower bound, saying you can't possibly be better than that. For example, if you want to find the minimum of an array, right, it's easy to convince yourself that you can't possibly do that faster than linear time. Because if you do it faster, then you skip something in the array. You can't look at every item in less than linear time. And if you skip even one item, if you skip even one item and you say the minimum is m, then I can say, no, it's actually m minus 1. You know, the item you didn't look at is m minus 1, and you can't prove me wrong. And that sort of approach is called the adversarial argument, saying that this is why you can't solve it faster than linear time. Well, that more or less concludes it for the big O. We'll use these ideas later, but let's now go to data structures. So much problem solving still, although I mentioned there are algorithms that are not really data structure related, perhaps. Much of problem solving is actually finding the right data structures. You should train yourself to really be snappy at this process of seeing a problem, seeing patterns in it, and knowing what data structures are appropriate for these patterns. Often the problem is of the sort where you have a sequence of things and you want to do something for each element of the sequence. And then the question is, what is the data structure that does that something the fastest? And well, here's a handy table, although I won't go through this table because I'll talk about these structures separately in more detail. But it's good to sort of memorize this sort of mapping where you understand, oh yeah, I have something order related here. I wonder if I can use a heap. Should be on the top of your head, of your mind. But without further ado, the data structures, specific ones, include in particular the very versatile hash maps and hash sets. Those are very commonly used. Should be your first instinct in many cases that if you are not constrained in space, you can probably memorize something, throw it in a hash map or a hash set, and you might save time on every element because you can avoid computing something. You store it instead. You compute it in the past, let's say. And in particular, you can store elements that you've seen previously, and that gives you, the solution to the counting distinct elements problem, for example. You can just throw in a hash set, and for each element, you can then very quickly answer in constant time, whether that you've seen that element. But they don't have to be elements, the values you store. You can do something more difficult. For example, the for-sum problem, which you may have seen, probably should see before you're interviewing, is problem of finding four elements in a sequence, which when summed together, sum to a particular target value that you're given. And you can solve that in quadratic time by going through every pair of elements, memorizing their sum, which means storing it in a hash map, that sum mapped to the indices of these elements, then going through each pair again, and again, looking at the sum, and then checking if the target minus that sum is in the hash map. If so, that means there's a pair of elements that sum to that. You take these indices and these four together, sum to the target. These are classical examples of the use of hash maps and hash sets. And on each slide, these data structures will have these complexities, and those are things you should know, right? That you can, in constant time, that's strictly not true. It's true for interviews. In constant time, you can say you can insert, find, delete in these data structures that are great, but they don't maintain order. That's the major limitation. Often you don't need order. And also you should consider that, these, they're very versatile, but sometimes you can do better than them. For example, if you want to count distinct characters in a string, well, let's say the string you're told only contains lowercase Latin characters, and there are only 26 possible values. Should you use a hash set for that? You can, but it's not the most optimal thing. You can use a bit set. You can use sort of something like vector bool in C++. A vector bool has ugliness to it, but something like that. You can use 132-bit int and bit masking, and that's enough. It's very space efficient, constant space essentially, because you have a constant number, constantly sized alphabet, and that's something some companies will want you to mention. Bloomberg, for example, in the interviews with them, I did something with hash map, and they said, "Do you need a hash map?" And I saw that, oh, I didn't need it. I needed an array of size 26. So, you should keep that in mind too if you're interviewing for a company like that. Then there are stacks. Stacks are pretty simple. The idea is that stacks, you can implement it as an array. You add something to the end, you remove something from the end, and because you can do it smartly in the way that you keep some extra space in your array, and whenever you run into the space, you double the size of the array, and when you have a certain number of vacancies, you halve the size of the array. If you do that, then it's true that adding items and removing items from the end are both constant time, on amortized constant time. So on average, each such operation is constant time. And stacks are useful for, broadly speaking, parsing questions. Like they're very much used in everything that has to do with that. Like if you implement some sort of, inverse, like postfix notation calculator, for example, or something like that, or even a real calculator, you probably use stacks somewhere. More easily, an easier example is, match parentheses, the match parentheses problem, where you have multiple kinds of brackets, like around, square, etc., and you need to determine if a string has them correctly balanced. Use a stack to solve that, for example. Another example is depth first search. It's kind of contrived. You can say you could do it recursively, but there are some cases when you might not want to use recursion. You might want to use an explicit stack, such as, if you might go really deeply into a graph and you run out of stack space. Where by stack space, I mean the actual, on the operating system stack. Then that more or less covers it. I can't really think of many more uses for them in interview questions. Queues are, in some sense, the other kind of structure that is similar to stacks, except it's the other way around. So stacks, what you just pushed, you pop immediately. And the queues, what you just pushed, will be the last thing you pop when you go through everything. So that's what first in, first out, and last in, last out, or last in, first out sort of terms mean. And queues, again, I can't think of too many things that you would use them for, but you do use them for things, where you traverse some structures in a certain way. For example, the breadth first search in a graph, you would use a queue for that. And this is immediate from the fact of from what you're doing here, right? Because breadth first search says, you see a bunch of things, and then when you take the first step, then you want to look at the second thing that you saw the first time, right? So this immediately maps to the situation with queues, where you go first in, first out in order of things, in the order that you saw the things. Heaps are very, very versatile and very, I think, underrated in a way. Like there's not too much attention to heaps, but they are great. They come up reasonably often in problems. And heaps, as I said previously, sort of alluded to, they kind of track ordering. That's the sort of morally what they do. That's kind of imprecise, but you should see a few problems with them, then you can pattern match what they do to the problems. And this is the first structure here that sort of doesn't have constant runtimes for relevant operations, meaning you have to pay a bit for inserting and deleting things. But it's really the constant time operation is finding the minimum of the things stored in the heap, or the maximum. Really, you can very easily have an implementation that does maximum or minimum by changing the sign if you really want it. So that's not the hard part. And the hard part, actually, something that isn't mentioned here, is that you can convert an array to a heap. If you can modify the array in place, you can in place convert to a heap in O of n time, which is useful, right? If you ever have a problem where you want everything in the array to be in a heap, then you can do that faster than naively inserting every element into an empty heap. That's kind of important, actually. Then what you can use them for is, as I said, all things ordering related. For example, if you want to find the top k or the top, so the largest k elements in an array, then one way you can do that is by maintaining a heap of size k, a min heap of size k. So the heap that tracks the minimum. And what you do is you first put the first k things in the array into the heap. That's fine. And then from that point on, you look at each element and you ask, is that element larger than the minimum of the heap? If so, then you remove the minimum from the heap and you add that element to the heap. And so that means that at all times, the heap keeps the k largest elements seen so far in the array. And when you finish this, you'll have the k largest element in the array in total. Another question, and I've had that question at least twice, the top k question. But another question is a streaming median. I've had that once, and it's a very interesting case, and I think you should know this just to get a feel for what heaps are. It's a bit unexpected, and I'll just say it in words. None of this I implement because you can very easily search these questions. They are online. Streaming median, the idea is that you see elements one by one, and after you see each element, you might get asked multiple times, what is the median of the elements seen so far? How can you do that efficiently? And you can do it efficiently by keeping, it turns out, right, it's not an easy thing to notice, but it's a smart use of heaps, that you can keep two balanced heaps, right? One sort of maintains the lower half of your items, the other the upper half. And so the one that keeps the upper half is the min heap, and the one that keeps the lower half is the max heap. And therefore, if you keep them balanced, then the median is either one of these elements, the min or max, which you can get in constant time, or it's their average. That's sort of the idea. There's implementation concerns, but that's more or less it. And linked lists are the last data structure probably that has some use, although they're not used often at all. And the virtue of linked lists is that if you have a pointer to a specific node in it, and what they are is just a chain of nodes, right? Value and pointer to the next one. That's a single linked list at least. And the virtue is that if you have a pointer to a node, then you can insert something after that node or delete the next node in constant time, right? Which you cannot do, for example, in an array or most other data structures. You can't remove from a tree in constant time, but you can from linked list. And one particular place where that comes up is the LRU cache problem, which is somewhat common. I know multiple people who saw it in their interviews, and it's highly rated on LeetCode, so it's pretty popular. You should know that solution with linked list and hash map. And more common, I guess, in the lower terms are questions that don't really require to use it to solve problems, but are about linked lists. Like I've had in 2A, I think, multiple problems of the sort of, how to delete a node from linked list. It's not a difficult algorithmic problem. It just shows that you can handle edge cases, right? Like you understand, like, what if you delete the first node, right? It's a bit different there, right? It can be different depending how you implement it. You should know that. You should know how to find loops also. I've had that asked only once, but it's also in CTCI. It's, I think, a somewhat common problem. And that solution, just to give you an idea, is to have two pointers, one lagging, one leading, they say. It's like one pointer moves by increments of two nodes, one moves by increments of one node. So it turns out that if you do that, then if they meet, then you have a loop. And if you have a loop, then they meet. So that's not obvious why that is true. CTCI explains why, but that's a handy thing to know. Okay, and then there are BSTs. I actually didn't list them previously because I cannot think of really any kind of problem that required their use in my interviews. Never used them to solve problems, but there are problems about them, mostly about traversing them. That said, the thing that they're useful for in principle is that they are an easily updatable ordered collection. You can see that, doing anything in this tree is sort of logarithmic, right? Which is not the best thing possible. Best possible is constant, but it's a nifty trade-off, right? You can insert into an ordered thing in log n time. If you had an ordered array, for example, you couldn't do that, right? You would have to shift things. So that's their virtue. And traversals are reasonably easy. What I mean by that is, you need to only see them once. For example, many problems involving trees involve some recursion. So you should know recursion. If you took CS135, you should be ready for that. Things like, how to find the height of a tree, right? You look, base case is leaf, it has height 0. Then any other node that's not a leaf, you take the height of left, height of right, you recurse into them, take their maximum, add 1. So that's not too difficult. And problems will probably be of that sort. I've had some more difficult ones. They are ad hoc. Can't really cover them generically. One important thing though is that BST, why is it useful? Is because it's ordered, right? If you traverse it in order, you mean you first go left, then you print. So you first recurse in the left part, then you do something with the root, then you recurse in the right part, then you'll see values in sorted order. That's the useful property. But for that to be true, the tree has to be a binary search tree. And how to determine if it's a binary search tree is not immediately obvious. For example, this tree is not a binary search tree because there's an 8 in the left, so it's smaller than 5. It's greater than 5. So it's this ordering is not preserved. But if you check this naively, if you say tree is a BST, if for each root the left child is smaller than the root and the right child is larger than the root, and otherwise, if that holds true, then you can recurse, then that's not enough, right? Because you miss this part. This is true for this tree, but it is not a binary search tree, right? You need to remember what is the range of all values that are allowable in this subtree is. That's a subtlety. I won't show code. You can find that also. Just keep in mind this potentially stumbling block. Okay, so now algorithms. That's it for data structures. I covered pretty much all I could think of that's appropriate for the level. Fundamental algorithms are very few because some more difficult ones may be used, but there's a great number of them. You can't cover them all. These you'll likely see at least one of them. All of them are useful in interviews. Sorting, I don't need to explain why sorting is useful, but in problems you might use it, for example, for cases where you really can't, for example, use data structure, right? Most obviously, if you want to remove duplicates from a list or a sequence, right, whatever way it's stored, you can use a set, like I said before, but the interviewer might say, okay, can you do this without using extra space, right? That's sometimes relevant, actually, and because you may avoid allocations, it's relevant in applied context. And if you want to do that, then the way to do that is to sort your, collection and then skip repeated items in it. So sorting is useful at least for that. Binary search is very useful for many reasons, but most straightforwardly, if you have a sorted collection, then you can search in it in logarithmic time in the size of the collection, which is great. Always, when you see that something is sorted, you should think, oh, maybe I can binary search somewhere here. Then quick select is the least commonly used of these, but it is used in some cases, and it's good to keep it in mind because you can there can be follow-ups. For example, in one of the cases where I had the top k question, largest k elements in a sequence, I was actually asked to follow up. Can you do this better time than you showed? Because with heaps, as I said, inserting into a heap or deleting from a heap is logarithmic in the size of the heap, and you do this potentially for every element, so it's O of n log k time total. You need to do better than O of n log k time, and you can, but it's subtle. The solution is quick select, because you can't always use it, but if you can modify the array, right? If everything's stored in the array, and you can modify it in place. If you're allowed to do that, then you can do this. You can do quick select, kth largest element, and it has the property that everything, it returns you the index of the element in the array, but it has now split it so that the k greater elements are all on the right of that element. So you can just output them starting from that index. And quick select is O of n, so it's a more efficient solution. I didn't think of that. Don't be me, think of that. Okay, that's algorithms. And actually, this is a follow-up to binary search. I just mentioned it, but there is a variation of it that is very useful in a kind of a different context. And the idea behind the variation is that you can use it more generally, not just for searching the collection, but for converting sort of decisional problems into optimization problems. If you can determine quickly whether something is true for an input, then you can find the first input for which it stops being true, for example. For this, you need the property that, as the input increases, you need this monotonicity, right? So for all the inputs it's true, then from some point on it starts being false for all the other inputs. And you can view this as binary search in a in an array of zeros and ones for simplicity. But binary search itself doesn't quite do that, right? Because if you binary search for one, then it's going to return you any one of the ones, not the first one necessarily. There's a variation of the binary search, which is called the lower bound binary search. In C++, called std lower bound. And here's an implementation here in Python. And this is something that will come up occasionally, and maybe I'll give examples if I have time at the end. Actually, this brings to mind something, namely, when you interview, you will sometimes have a choice of programming language. Often, actually, have a choice of programming language. Good language to do your interview in is Python. Even if you don't know Python, you haven't used it before, it's not a difficult language to learn. Just learn it in some capacity. You don't need to be an expert in it well enough to use it in an interview. That will save you a lot of time in many cases, right? Because it reads like pseudocode and it's written like pseudocode, and just as a very practical thing. Many of my peers have told me that they used to interview in another language, then they switched to Python. It's peer approved. It's a great idea. And all the rest of my code in this presentation will also be in Python, by the way. Okay, so that's it actually for data structures. Now there's a topic I want to cover that's not data structures and not these basic algorithms, and that's dynamic programming. Now you won't necessarily have many questions that are GP based in your lower terms. I did have questions in 2A. In my 1B term, in fact, I didn't have any algorithmic questions. And moreover, all of the jobs I've done so far, I got them without doing algorithms. So the interviews for those jobs did not involve algorithms, actually, surprisingly, although I did have algorithmic questions for many other jobs. So especially for lower terms, it might be the case. But in 2A, I already had DP, so it's a good thing. You should know it. Maybe don't pay as much attention to this, the rest, because it's more upper term topic, but it's still good to know. So the core idea of DP really is that a lot of problem solving, a lot of optimization, running things more efficiently is based on the idea that you duplicate some work. You shouldn't do that. Don't do anything twice. That's the core idea. And DP is exactly about that, right? You have problems often that naturally split into problems of smaller size but the same kind. For example, if you compute Fibonacci numbers, this right here is the call tree of a computation tree of a naive Fibonacci number computation. The nth Fibonacci number is defined as the n minus second and n plus n minus first, and with base cases for 0 and 1. So naively, you can implement it in this way, where you just recurse on the one input and the other. I'm sure you've seen this, and I'm sure you've seen why this is bad, because this huge call tree, right? This huge computation tree. It's bad. It's slow. It's exponential, in fact. But you see that there are many repeated problems, right? There are subproblems. You see all the ones that are highlighted in the same color here are the same problem. So you can do this much faster if you just somehow remember them globally, right? Once you've solved fn-1, you never solve it again. You just look up the value and use it. And that's a very straightforward way to do that, which is putting something in a map, right? Let's say I'll go to that later. But the last sort of comment on this is that actually I forgot to mention, but some companies are known for using DP, right? So if you have an interview with that company, you probably should actually pay more attention to it. For example, I've heard that Google actually focuses on DP. I'm a bit cautious giving that advice because it wasn't true for me. When I interviewed with them, I didn't have DP, but it is something that a lot of people say. So I presume there is some truth to it. If you have Google, it might be wise to look into this more deeply. But anyway, onward with this idea, right? So you can throw things in a hash map. You can have some global hash map where you store the values as soon as you compute them. And if you when you compute something, you check if you've seen the input. If so, you return the value. Okay, that's one way to do DP, which is what I mean by memorized solutions. But there's another way to do it. There are two ways, broadly speaking. There's the top-down way, which is this, You start with what you want, with n, you descend in subproblems, so you recurse into fn-2, fn-1, etc., and you use something like hash map to memorize, values of c. So this is a very intuitive way to do this, because it immediately follows from, let's say, the definition of Fibonacci number computation in this case. So that's a good starting point when you solve the problem. And it can also actually be the most efficient way if if very few of these subproblems are actually needed. In this case, you solve everything from fn to f1, right? But in many cases, you'll skip many problems. Maybe you skip most problems of subproblems of smaller size. If you do that, and if it's hard to know ahead of time how this works out, then maybe this is actually a good way to implement things. You'll see an example later. And the other approach is bottom up, where you start with the base cases. In the Fibonacci cases, f0, f1, they're given to you, and you build up your solution by solving larger and larger subproblems, starting from the small ones, until you arrive to your target. At this point, you've solved all the previous ones, and you can, use the memorized values to solve the target one. This is generally more efficient in the sense that, well, in some senses, I mean, sometimes you can optimize things smartly in this case, in a way that you couldn't easily do in the top-down case. But more generically, you avoid recursion, right? Something I haven't really talked in depth about, the way why recursion sometimes is expensive, but the core idea is that whenever you recurse, you use some call stack space, and call stack space is usually limited by the operating system to some, bounded amount, constant usually for a program. You can increase it, but most programs don't, and you will crash if you run out of it. So, and languages like Python actually limited at even smaller values. So you can't recurse too deeply unless you have a language that works well with that. So, and even then, some cases of recursion are not fixable in that way. So sometimes you just can't avoid paying with stack. And the bottom-up approach, because it doesn't need to recurse, it can work iteratively, it doesn't use that stack space, which is good. They say usually bottom-up, as a rule, is more performant, more efficient. And here's the example of the Fibonacci case. There's a top-down, there's a bottom-up approach. This add cache here, that's a Python thing. There's a module called functools, which contains the cache function, which you can add as a decorator, like here. And I've used this in interviews, and people were fine with that. That's a brief notation you can use to just say that I memorize the computation of this function, right? So whenever I call the function, what this does is it wraps it implicitly in a thing which looks at the arguments, hashes the arguments, and it has an internal hash map, and it checks that and sees if you've seen these arguments before. If you haven't, it returns what the function returned previously. So that just avoids the boilerplate. All right, this is exactly the recursive implementation, which is inefficient, but yeah, I slapped it on, and now it's efficient, more or less efficient. Well, the second approach is the other approach, the bottom-up approach, where I start with 0 and 1, which is the 0th and 1th values of Fibonacci numbers, and I build up. And you can obviously see that that approach has at least one obvious benefit, which is that you don't have any, you use constant space. And this is because it kind of cheated. I already optimized it a step further, right? Because the most straightforward approach would be to just keep an array of size n, where 0th and 1st entries are set, and then you set the entries in the array. But then you immediately notice, I only use the previous entry, right? So I don't need to store the whole array, and this is already the optimized version. It's faster generally, and it uses constant space, which is great. It's a common theme. For a more difficult dynamic programming question, I'll present to you the longest common subsequence, and it's more challenging, but also something you might see in reality. It's not a purely academic problem. I've had it in interviews, and the longest common subsequence asks you, you have two sequences, let's say two strings of characters, and you want to find, you want to find a string such that you can remove, which is formed when you remove some characters from the first one and from the second one, Okay, I kind of phrased it badly. So let's say you can remove some characters from the first string and from the second string. The question is, what is the longest string you can get as a result, such that that first string and the second string matches? Yeah, it's kind of difficult to understand from words, but right in the slide you see an illustration of that, right? You threw out some characters and you got the same string A, B, C, D, E, and that's the longest one you can possibly get in this way for these two inputs. Okay, that's the idea. And right down below you see a natural implementation of that, that follows from the sort of definition. It's not quite immediate, but it's something you could deduce, right? You look at the strings and you say, well, the only time you increase the length of the common substring is when you have two positions that match, right? Because those two go into the answer. So that is the case where you sort of pop characters from the ends of both substrings, and you add one when the characters match. Otherwise, you say I need to step on one of the strings because until I find something that matches, right? At least one of the strings. We don't know which one, which is why we have this fork here at the end, which is why it's not a trivial problem, because you need to consider both possibilities. Maybe you need to skip one here, maybe you need to skip one there. No, also maybe that was a bit too much at once, but you can start it more carefully. You have slides and you can convince yourself that this is true. This is the right way to solve it. But this is not an efficient way because, first of all, in Python, when you take a substring, when you pop the last character, Python stupidly copies the string for some reason. So just doing that slicing is already non-constant time. And also, obviously, the more grave problem is that you actually branch a lot. When you draw the call tree, you'll see that it's also, it has exponential size like Fibonacci, so it's no good. But we didn't do any DP yet. Why is this DP? Because you can more or less slap on a cache on it, and again, it becomes efficient. Actually, you could slap on a cache right here. It still is decent, but it's not that good because, again, as I said, slicing the string is not constant, but also what the cache does, as I said, it looks up the inputs in a hash map. And hashing strings is also not constant time. So you don't want to operate on strings. But a pattern that you can use also in other problems is you can have a higher level function, so sort of like parent function that has the strings, takes in the strings and its inputs. Now they're in scope. And now you have an inner function which can see the strings, but it doesn't hold on to them. Instead, it only operates on indices into the strings. And in this way, you avoid paying that cost of copying and hashing the whole strings. You just operate on indices which are integers, and that's much faster. And this is exactly the same implementation, exactly the same idea, except translated in this way. And now it's efficient. Now it's no longer exponential. It is, it can be quadratic or actually, well, with luck, right? Imagine if the strings are exactly the same, it's linear immediately because only the first branch is ever taken. Okay, so there's that, and that is the top-down approach because you start from the end. The other approach is the bottom-up approach again, where you translate the problem. See, they're also very similar. The if statement is, well, it's practically the same inside there. So you see the duality between them. They're very close. But the bottom-up approach in this case actually turns out to be kind of unfortunate, like this immediate implementation, because what you see here is that the base cases, which are explicit here, the base cases when the strings are empty, when you have popped everything from one and from the other, you come to a zero-length string and you're done. Here, the base case is kind of implicit here. This LCS array, right? It's size n plus 1 times n plus 1. So it's like a matrix, really, 2D array. And your base cases are zeros, right? So if one string is empty, then the answer is 0 again. And then this for loop goes through, endings, substring endings that aren't 0, that don't result in 0-length string, and it computes this optimal, length of the longest common substring in the same way, using the same sort of decomposition to some problems. But the problem with this is that it's always quadratic, right? This one could be linear with luck if this condition always was true. If the strings were identical, for example, this one won't be, right? Because there's a double for loop and there's no way to skip in it. So this seems kind of unfortunate, but actually, well, it is unfortunate, right? So this is an example where top-down may actually, benefit you because it's also easier to see. But at least, the storage space, again, the storage space would be linear in the previous case, but in this case, it doesn't have to be linear. In this case, it's quadratic right here, but it doesn't have to be. And a challenge to you, I guess I won't go over it, but it is actually possible to use only linear space with essentially this same implementation. See if you can find the approach. It's more or less the same idea as the Fibonacci one. Okay. So that's it for this problem. It's kind of much, but again, you have the slides. You can go back to it. There are many great problems on LeetCode on dynamic programming. Here are some, for example. Longest increasing subsequence actually is a very nice problem because it combines this dynamic programming with binary search. And this is also a question that was asked. I never had it, but the person I know actually had it in their interview. So also not purely academic, but there are some other ones, and there are plenty more tagged dynamic programming on LeetCode. So you can solve those at your leisure. And actually, that concludes it. That is all that I have. We'll do a mock interview now, and then after that we'll have Q&A. Let me jump into. Follow the link here. Link. Also, I'll stop sharing the slides. I'll share the interview tab.
Cool. I'll also help out for this mock interview and try to be a good interviewer.
Okay, I think this is the one. Let me do that. Yes, can you see that? This is a coder pad. Yes, actually, this is something you might very realistically use. I was asked during COVID interviewing season, I was asked most problems on coder pad. So that's your platform right here.
Cool. Okay. There's the default stuff. So
I'll delete that.
I will give you the question. So given a string, count how many palindromic substrings are in this string.
Okay. Right. Yeah. Usually also something you might do in a real interview. You can say a disclaimer. I've seen this problem before, but I don't exactly remember it. From this point on, sorry, I shouldn't have said that. I'll be in interview mode, so I won't provide meta commentary. Okay, I see. I guess my first question here would be, as I understand, you want to count sort of the number of sort of indices that define the boundaries of the substring, right? So it's not unique number of palindromic substrings, as in if you see, ABA, BAB rather, if you see BAB twice, that counts as two separate strings, though, substrings, if the indices are different, right?
Correct. Yeah, there can be duplicates. Okay.
Yeah. Okay, that makes sense. And the empty substring is not a palindromic substring.
Yeah, sure. We can assume that.
Sure. Okay. And I mean, nothing else. I suppose Another question I have is the characters. I'll use Python actually and remove that whole concern. I will comment though that anything that has to do with palindromes in a language that doesn't natively do Unicode might be tricky. It's good. I may assume, let's assume for this problem, if that's okay with you, that the characters are, let's say ASCII, right? 1-byte characters.
That's fine.
It shouldn't be a problem in Python. There might be some, I forget exactly how they do Unicode there. There might be some things. Okay. Yeah, so one way to solve this is there's a naive solution, which is, you look at every substring, so I need two distinct indices, define a substring, and you look at that and check if that's a palindrome. That works. That is cubic. There are n squared substrings, O of n squared substrings, and checking each one is O of n potentially. So O of n cubed in total. We can do better than that, I'm quite sure. We can't do better than O of n because you have to look at every character, I think. Right, because if you didn't, then you would, you could change the value and it would change the number of substrings. So it's linear at least. I don't know off the top of my head a linear time algorithm for this. I suspect it actually might be difficult, but let's see if I can do something here. So as I said, I've seen this problem before, and my impression from before is that it involves, one approach to it. I kind of vaguely remember. I don't exactly remember. Don't remember the code or anything, but I remember the idea behind it. And that approach is that you transform the problem to looking at centers of potential substrings. So what I mean, let's do an example here, right? Also make sure to understand the problem correctly. Something like, that is a trivial example, something like this, right? So it has each one character substring is palindromic, then BCB, this is so this is another substring palindromic, BCB here. Then this one, A, B, C, B, A is a palindrome. And so I think the idea is that you look at C, you look at each center and try to expand out as much as possible. And that way you can do better, right? Because if you're in the center and you expand, you can expand by at most, n over 2, which is the largest distance you can have to the edges. And so that's O of n, right? And there are O of n centers, so that should be quadratic, I think. Yeah. But yeah, it might be a bit tricky, the implementation. One way I could implement this is by, I think this is what I vaguely remember. One way you can make this easier on yourself is by having, just filling in the spaces between characters with some other character, and then just treating that character as a filler, because it makes, there's an edge case here, right? I think where if you have like a 2-character palindrome like this, DD here, then that's a palindromic substring, but you don't have a center here. That's kind of tricky. That, yeah. So let me implement it like that first. So I'll implement the centers idea, but I'll use these auxiliary characters, if that's okay with you.
Yeah.
Okay, and then I'll, if I have time, I'll transform it to the more efficient idea, which doesn't, copy anything. Let's see. Yeah, so the idea, let's say this is count palindromic substrings to be very verbose. There's a string that's the input. Let's call it S actually for brevity. And then the idea again is, I guess you would you would create a string that has characters in between. An efficient way to do this to avoid all the possible redundant copying in Python is I could use a byte array. Is that actually? I think that's too much. It's more than is necessary. I think there's a smarter idea, which is, let's say s is. So I'll use the hash character. That's my vague memory of it. Let's say hash. So we said lowercase ASCII, or we said ASCII characters, but hash is an ASCII character. So let's say maybe they are lowercase or Latin characters, right? Something like that. So it doesn't include punctuation.
Yeah, just the alphabet. It's fine.
Cool. So let's say then this character cannot occur in S in that case. And I can do something like join this, split S into characters and join on that, so it inserts it into each space between characters like that. I think, yeah, so it would be something like this. To illustrate what I mean is, see, this can now be a center of the substring. That's my idea. And yeah, let me just be a bit careful, because I noticed that if you do that, then you have to be a bit careful, I think, where you look at these hashes. You have to skip over them if you count strings. Like if you count from C, then you shouldn't count this one as a palindromic substring, because it's not in the string, right? It's the same as C without anything. You have to be a bit careful with this. Okay, so then this looks something like, let's say for I, yeah, so I want to use indices here actually, so I'll do something like for I in range length of S, which is now this new string. If, yeah, so now J is, yeah, I'll keep J as a counter, as a naked counter like that, I guess, and I'll check the bounds explicitly. So while I'll look at I minus J, that has to be at least 0, and I plus J is, let me call, let's say N is the length of S here. Then while this is true, then this is valid, but this is true, otherwise we'll go on the next iteration. And this means that we're looking at like, substring centered at D, like, or at C, like here, let's say. And so I first look at C itself, which is in case J is equal to 0. So if Si minus J, and whenever it's always symmetric, right? So whenever I minus J is a hash, then the I plus J also contains the hash. So I think I can just check 1, right? That has to be true, because yeah, any center is either a hash, in which case it's like the even elements, even indices. Otherwise, it's the odd indices that contain hashes. So they're symmetric. So if it is the hash, let's be consistent and use the same kind of quotation marks here, then I will, what will I do? Yeah, so it's a hash, then I skip it. I don't count hashes as palindromic substrings. Otherwise, if Si minus J is equal to Si plus J, then that means there's another substring here. 0, this is count increased by 1. This is correct. Let's see. Right, I skipped these, so that's right. And I think I stay in bounds here. Let's say tentatively return count. Let me just run through a test example here, because I'm not quite convinced this is right. It's a bit short, I would say, but maybe that's actually the right implementation. So say that let's try this example, right? I'm pretty sure that this does what I think it does, which it results in that. Then n is what? This is this is hard. This is 7 characters, and so 6 spaces. That's 13. N is equal to 13. Then the I don't necessarily need that fine granularity. I just need to see what happens here. This for loop is the part where it might be a bit complicated. Let's see. So start with I is equal to 0, j is equal to 0. So that's a. This is not true, so I count a. Good. Right, these both hold. And really, what can be an edge case here, right? Like it works at the boundary as far as I can see, because I don't j is 1. This is no longer less than or equal to 0, and this boundary also works. Actually, I think I'm comfortable. I'm comfortable enough to claim that this works. Should I write some programmatic tests to actually check this? I think I have time.
If you could write it quick enough.
Yeah. Okay. It will only take a moment. Well, this is kind of extraneous, actually. So assert. My love for big names is catching up to me. Let's say. So really, I should have kept the original string ABC, BADD. How many palindromic substrings does it actually have? I didn't count them, to be honest. Let's see, it is so again, A, B, C, B, A, D, D. This is 1, 2, 3, 4, 5, 6, 7. I just said 7 characters. Then this one, so 8. And that one is 9. And this one is 10. So I think this should be 10. And also, I guess an edge case is that the string is empty. I'm pretty sure it's a no-op if it's empty, because the for loop never does anything, but it's always nice to check that. Let's run this. I think this says that the assertions did not fail. I actually forget how GoTerPad works. Okay, it asks for input. Is that true? No, I guess not. This seems like it passed. Let me insert something that's obviously false. Oh, well, what do you know? It seems that I accidentally wrote something that is extremely complex and it failed. Yes, sorry. There's a bug here. No, wait. There's a bug here. That's right. Where I didn't increment j, of course. It's too smart to use this while loop here. Well, let's see. Another try. I claim that this now is correct. Wow. This takes a while. Not filling me with optimism. Oh, yes, of course. This is why I shouldn't do that. If this is not equal to j, then increment that, and otherwise do that. Yeah, this is still the same idea, but now I increment j every time, not just occasionally. Right, this is what I want. It's not equal, and those are equal. Yeah, then count plus equals 1. Okay. Well, what do you know? It's not 10. Let's see. this is pretty strange. Did I miss one? What is the right answer? 1. Well, okay. What do I produce?
Yeah.
Print count. Yeah. I think we're within time still. I mean, sorry everyone, but this is what happens. You know, when you have an unrehearsed problem, you may solve it very successfully immediately, or you may not. Let's see.
This is how interviews actually go.
I mean, ideally, it doesn't actually go like this. Ideally, you have you are more careful, but I was not very careful, and I'm paying for that. So it says there are 12. I don't see how that's possible. Let's see. Because okay, there are 7, right? There are 7 characters. One, then there's like another one and another one. There's DD. Am I missing any?
Are you looking at the wrong string? We're looking at this string, right?
Am I? Oh, geez, you're right. Does that change things? Yeah, it is different string. Okay, it's believable that there are 12 substrings here. But let me verify really quickly. 1, 2, 3, 4, 8. So 8 plus like 1 and wait, so plus 9 and 10 and 11 and 12. Okay, actually, my code is smarter than me. There are 12 substrings there. Okay, assertions did not fail, so this is correct. And we still have like at least 10 minutes for Q&A, which is great. Yeah, well, if you do this in a real interview, it's not a great performance, to be honest, I have to say. Ideally, you would notice this, like this in particular, when you actually solve the problem. I guess get a bit overconfident because I thought, oh, I know this problem. I mean, I've seen it, right? And I have an idea of how to do it, but I don't actually, I didn't like write the code ahead of time, so I missed this thing. Ideally, you would be more careful than I was, but this is an all right performance from me, I dare say.
Yeah, I'd also recommend like writing comments in between your code as you code, if you have extra time, like in an actual interview, just to like, I don't know, tell your interviewer what to do. But anyways, that was good.
I usually just narrate, and that works well for me. I don't never had that suggestion voiced to me, but it can work well if you have time, right? Usually everything hinges on time.
Yeah.
If you have a lot of extra time, then that's a big luxury for you. You're lucky you can use it to show off, like write comments. It's great. Yeah.
It helps sometimes, but
yes.
Anyways,
that's it with the mock interview.
Yeah. So we will go on and do a bit of Q&A.
See that my video is turned off actually.
Yeah.
Was it turned off the whole time?
I think so.
Oh, okay. Well, that's great. You don't really need to see me. I now that I turned it on, I guess I'll keep it on. You didn't really need to see me.
But anyways, if people want to ask questions, Slido is on the screen, or the Slido link is on the screen. I'll just go through the couple questions that are here already. So the first question is, what should I do if I can't think of a solution within the first 10 minutes or so?
Usually in most interviews I've had, you'll get hints before then. Like they won't let you stay around and think for too long, or even sort of tentatively propose things for too long. If within some time frame you don't produce anything, they'll give you hints. It's not a terrible thing, by the way. I've gotten offers from interviews where I had hints. It's not, doesn't mean that they're pitting you to end the interview. It actually is a normal thing. And it's kind of on the interviewers to avoid, that stalemate. If they give you many hints and you don't get the problem, that's more severe. I don't think there's an easy way out. The interviewers are supposed to kind of handle that situation. Right? That's not easy to handle as an interviewee. If you just don't know how to solve a problem, they should give you a way out eventually.
Yeah, I think they do quite a bit of guidance, and like honestly, at some point, like if you really can't think of something, I'd say just brute force it. Like find the simplest like method that you can and just do it. Just like show you can do something. And and if there's anything else, then your interviewer will probably guide you through. Cool. So next question is, in an interview, what's the process you have right when the question is presented to you? Oh, that's in the slides if you wanted to see that. And you can refer back to it if you want. But typically, it's the classic, like you talk about the question, you ask edge cases. I don't know, Dimitri, if you want to talk about this.
Yeah, I mean, I navigate to that slide in my screen sharing, but yeah, I usually do that. As you saw actually in this interview, I maybe wasn't too careful following this. I don't follow things very closely usually. I ad-lib a lot. That's a weakness, I think, in some ways. Maybe in some ways a strength, but I don't. I usually always, before I write anything, though, I voice what I'm going to do. If I see a problem that I know very well, then I'll just say, "Oh, I know this problem. It's this and that, and the approach that is optimal for it is this one." Right? I'm straightforward with it. I actually got burned a few times by it when I said, "I know this problem." They said, "Oh, great, we'll give you a more difficult problem." And I didn't get that one, and I didn't get the job. It can burn you in that way, but mostly people appreciate it, I think. But otherwise, yeah, I just more or less follow this list, right? I actually picked up from Discord because it's a great list. I think it reflects, thanks to Jennifer, it reflects the process very well.
Yeah, I think you basically did that. Like I was writing notes during the interview, and
Hmm.
you basically did every step of this. Like you asked questions for things that weren't exactly clear. You talked about the edge cases. You talked about like what types of inputs were in there. You also stated assumptions, which are really good, and talked about runtimes for everything. And I'm sure you get like little brownie points for just like even thinking about just like making tests and making it like testable so you know that your code works.
Yeah.
But yeah. Anyways, that segues nicely into what should I do if I get a question I've already seen? Do I let the interviewer know?
Right. I guess I kind of half answered that. My policy is to do that because I think it's difficult to convincingly pretend that you haven't seen it if you have, or, that's a risk you take, right? I don't take that risk because I don't think I'm that good of an actor, to be honest. But it can burn you, like I said. It's usually people appreciate it, right? Like I've had, I sometimes said that, I've seen this question. They said, "Oh, solve it anyway, but thanks for telling us." In which case, it was great, right? They appreciate it, and it's easy. It's an easy question for you to solve. That was almost every instance, actually. There was only one. They might give you a different question of comparable difficulty sometimes, which is like a small loss, I guess. But again, it depends on if you want to risk it. There was only one case where they gave me a much harder question instead, and that was unfortunate. But unfortunate things sometimes happen, right? If you have in many interviews, eventually you'll have interviews which are just bad, or no fault of yours.
Typically you'd want to tell the interviewer about it. And for some companies, like, I don't know, I just know Google, but like they give you just a little brownie point for, just being a good person, basically, and letting them know. But yeah, let's see. Okay, there's a question on Twitch actually, which is, how do you guys look for which LeetCode questions to do?
Right. So one answer to that is there are list and discuss, which there's quite a few discussion posts on LeetCode actually. There's a vibrant community, and they compile questions which they think companies ask. You can also look on Glassdoor. That's if you're targeting a company. You can also have LeetCode Premium. I actually had LeetCode Premium for a month once when I really was determined to get a good company under my belt. It was worthwhile for me, I think, because also it motivates you to do LeetCode because you think of all the money spent on it. And you're like, well, I must now use it. Otherwise, what did I pay for? And also then you get access to, those like secret tags, questions tag Google, etc. But there are other ways to get that information. But yeah, there are lists going around of that. Otherwise, there are also lists of fundamental problems that are common between companies. Also in LeetCode, I found one like 2 years ago when I did them. Probably there are better ones now, maybe. You can just search for those.
Yeah. I find that if this isn't like a cramming a couple days before the interview type of thing, and you do just want to go through like a couple LeetCode questions just regularly, then daily coding problem works very well. They send you like a LeetCode question every day, and you can like take a look and you can solve it, and they're usually fairly relevant questions, so that could help. But yeah, anyways, next question. This question says, do I need to solve the question every time?
No, you mean in an interview? No, I have received offers. Maybe I don't know how many. I forget exactly, but it was at least one occasion where I received an offer after not having solved the question in the interview. So it's not a hard no. Did they really expect you to solve it? That doesn't do you credit, but sometimes they will ask a question that's out there, see if you can solve it. And if you don't, then that's fine.
Yeah, often if they can like just see your, I don't know, working process, how you problem solve, that's enough. And then you can get an offer from that. Best case scenario, you solve the question, but you don't really necessarily need to in order to get an offer. Okay. And what advice would you give to a first-year student who doesn't have much programming experience when it comes to full use of LeetCode?
I mean, two things I would say. One thing is, we just did this presentation, but actually, if you're in 1B, then likely won't be asked very difficult problems. As I said, I wasn't asked anything, algorithmic at all in 1B. Some people confirm my experience. If you had a really good company interview, then maybe it will be. But you shouldn't expect to be, given longest increasing subsequence in 1B. Almost certainly not going to happen. But otherwise, just doing LeetCode is good because you do have to code there, right? And you see your ranking, you see the efficiency of your solution compared to other people who submitted. You can optimize it, in that way. If you mean just to learn, languages in general, it's different. I'm not sure if that's the right interpretation of the question. What do you think, Colin?
I don't know. I think probably the best way to use LeetCode as a first year would just be like making sure that you can do most of the LeetCode easies, and then trying out mediums that are like highly upvoted, because those are usually common. And yeah, just going through problems. I don't think there's any like trick to it. But also, yeah, I think that first year interviews usually don't have very difficult questions. So just being able to do like most LeetCode easies, some mediums, you should be fine. Yeah. Cool. Oh, and one more thing. I think we should recommend people to also go through some mock interviews. Mock interviews are very helpful because someone else can see like how you're doing and like what you're doing, and give you like input before you actually do a meaningful interview. So definitely sign up for mock interviewers, whether it's like with Tech Plus. Their mock interview sessions are, I think, like this following week. Or some other organization, or just your friends, like just recruit your friends and like interview each other. It's very helpful just to like go through different problems and kind of go through the process. And it helps with the nerves as well if you're prepared for like what it feels like to do an interview. Yeah, but I think that's all the questions we have for today. Do you have any other tips or advice, Dmitro?
I guess not particular. Maybe one thing is that it's difficult to be not nervous during an interview, especially if it's a company you really want, and they're known for hard interviews. Often these things are correlated. Then correlated is the right word. It's difficult to stay sort of not nervous, and I sort of brainwashed myself into not being nervous, I think, over time. And yeah, I don't know a better tip actually than that, which is, this is a super random aside. Sorry if it's actually not fit for this, but it was helpful. It would have been helpful for me to hear this, I think, And I actually found a niche. For me, it's cryptography, which I can learn well, on a level that I think is sort of above many, and that sort of instilled me this fake confidence, right? I'm not good at algorithms, actually, not that good. I'm not competitive algorithmist, but I just convinced myself that I'm incredibly great, and sort of now I feel confident in interviews because I'm like, I'm great. Obviously, I can do this, even when it's unfounded, right? I've had interviews which I actually did badly in. One of them I had an interview where there was a problem and I solved pretty much none of it. I was ill prepared for it and was not feeling well, and so it was a total disaster. And I didn't even feel like it was a total disaster. I just felt like, there's a person on the other side of the phone, but what do they know? A super random thing, actually. I'm sorry if this isn't fit for this, but it helped me a lot, right? I was way more nervous in terms before I did that. I wish I would have known this.
Yeah, I think that's helpful. I think definitely go into interviews being confident, but know that there are just going to be some interviews where you can't do it, or it's just going to flop, and you're going to have a bunch of those. So yeah, just try to prepare as much as you can, but don't be, I don't know, don't be too sad at bad interviews. They do happen. They happen to all of us all the time. But yeah, anyways, I think that's all we have for today. Went a bit over, but I hope that was useful. All the slides will be available wherever at bit.ly UWCS Club / CTCI136 slides. And yeah, we'll post this on YouTube later. If anyone has any other questions or need any other help, feel free to join our Discord. We're always available. Be sure to get your mock interviews in. So Tech Plus is running mock interviews. Be sure to do that. And our next event is on Thursday for basically starting our after hours series, where we talk about a bunch of really cool, not really cool, but just some topics that we usually don't normally talk about. Some regarding mental health, some regarding just failing courses, having a hard time. We'll have a couple speakers for that, and we'd love it if you could join us. So yeah, that's all we have for today. Goodbye, and thanks for tuning in.